In this session, we're going to talk about perceptrons. This is course contents. First of all, we're going to talk about the motivation of perceptrons. And after that, we're going to discuss multi-layer perceptrons. And then we're going to have a look at vectorization. And finally, we're going to talk about learning MLP. Basically, MLP is a stack of multiple perceptrons. Therefore, we are first going to talk about a single perceptron. After that, we're going to stack them and make them as multi-layer perceptrons. And vectorization is one of the techniques to accelerate the computation. And because we are dealing with a lot of matrices, vectorization can improve the efficiency in a great deal. After all, we're going to talk about learning MLP. Rather than setting the parameters of MLP, we're going to learn those parameters from data. After that, we're going to summarize the lecture. Before we move on to our contents, let's see where we are now. I told you in the previous lectures that these 5 steps are general steps for building AI models, ML or DL, machine learning or deep learning. The first step was data preparation. And after preparing the data for our models, we actually need to build models. And we're going to use neural networks. And then we're going to train our models from the data we prepared. And after trained our data, we need to evaluate those models. If you're satisfied, we don't have to go to the step 5. However, in general, the performance of our models are not satisfactory in the first hand. Therefore, we go back to the first or second or third steps to improve the performance. So these are 5 steps, and we are talking about the second step, building models. And basically, today we discuss perceptrons, and later on, we're going to discuss more advanced and complicated models. All right, then let's discuss the motivation of perceptrons. I mentioned that machine learning is a type of function approximation. And what kind of function? We're using this function to model the relation between input and output. And to design this function, we're going to use various types of computational components. And I'll introduce some of these components as we proceed. And to give you an example, let's say we have these 3 types of input. A picture of a cat, an audio signal, and a German sentence. Es gibt keine Grenzen, nur Möglichkeiten. And let's say we have a machine learning model. And I told you that this machine learning model is a type of function. And using this function, we want to map the inputs to the outputs. For instance, we might want this type of output for the first input. A cat is wearing glasses. This is one example, description of the picture. And the second sentence, the second output is the spoken language. And from this audio signal, we want to transcript the audio. I am very, very happy today having fun. And let's say we want to translate this German language into Korean language. And we can do these things using our machine learning algorithms or deep learning algorithms. By the way, how can you model these effects? In our paradigm, how we are dealing with these modeling problem is by parameterizing the function with W. And we're going to learn these parameters from data. And I gave you this example. Let's say for the input X, a linear model will map this X into an output Y using A and B. Here, A and B are in this parameter set. And rather than setting these values for A and B, we're going to learn these values from data. And this is just a simple example. And in real world, what we are doing is we have millions of parameters. And we cannot set all these values by ourselves. Therefore, we're going to use data to find the proper values for each parameter. That's what we are going to do. And the very first model that researchers came up with is this simple perceptron. And here, let's say the input has dimension m. Here should be xm. And for this m-dimensional input vector, n-dimensional input, what we do is perform weighted sum. And weighted sum is not a complicated thing, but a simply x1 times w1 plus x2 times w2. And we do this up to xm. And this is the weighted sum. And after we get this value, let's say this value is y hat, we're going to threshold this value. And if this value, y hat, is smaller than this threshold, we're going to, here, binary signal means the output can have only 0 or 1. No other values are allowed. Anyway, if y hat is smaller than t, let's say this binary signal is going to be 0. On the other hand, it's going to have the value of 1. So this was the very first perceptron model that researchers came with. This is another view. I told you that we are going to parameterize this function, our model. And here, W1, W2, and we can have extra value, which is bias. And this B are all parameters. And we can represent this operation using matrix multiplication like this. Here, W is W1 and W2, and X is X1 and X2. And as you can see here, W and X, they have the same dimension. So as to allow dot product between these two vectors. And we have a scalar bias. And why did researchers try to come up with some type of perceptrons? The goal of developing these models was to successfully develop mathematical or computational logical gates. Why were they concerned about logical gates? Logical gates are like AND or XOR or NAND, things like this. Why were they interested in these types of gates? Because if you could implement one of these, especially the NAND gate, then you can actually implement a whole computer system. This is the basic of computer engineering. You can come up with all types of computer hardwares once you can come up with the NAND architecture. You can combine NAND gates in various ways, and then you can come up with a computer. So that's why researchers were interested in implementing these gates, logical gates. And here, we're going to have a look at the AND gate first. What is AND gate? When the inputs are not 1 and 1, then the outputs are zeros. However, when x1 is 1 and x2 is 1, then the output is going to be 1. So you can view 0 as false and 1 as true. And how do we implement this AND gate using our perceptron? By setting W1 as 1 and W2 as 1, and the threshold as 1.5, we can successfully implement the AND gate. So to give you some examples, let's talk about this case. When x1 is 0, W1 is going to be 1, and x2 is 1, and W2 is 1, then the output is 1. And because this value is smaller than 1.5, it's going to become 0. However, in this case, 1 time W1 plus 1 time W2 is 2. This is larger than 1.5. Because this value is larger than the threshold, it's going to become 1. Very simple. You can view this in another way. You can think of it as W transpose and X are dot producted in this way. And if this value is larger than minus W0, which is 1.5 here, then it's going to become 1, otherwise 0. And you can plot this on this graph, on this space. And what you need to do is distinguish these 3 points from this one. To do so, you need to draw a line that looks like this. And you can perfectly model this line using this relation. So x1 plus x2 and 1.5. Here you are multiplying 1 and 1 here. And compare this value with 1.5. In the case of OR gate, you can set W1 as 1 and W2 as 1 as well. Here, you're changing the value of the threshold. In this case, the threshold will have 0.5. And in this case, 1 times W1, which is 1, plus 1 times W2, which is 1. It's going to be 2, which is way larger than 1.5, and it becomes 1. In the first case, 0 times 1 plus 0 times 1, which is 0, which is smaller than 0.5, and it's going to become 0. Easy peasy. You can also view this on this graph. You need to distinguish these 3 points. I'm bad at drawing from this 1 point, and you can draw this line to distinguish these points from this point. And you can view this as this line, 1 times x1 plus 1 times x2, and compare this value. If this one is larger or smaller or equal, then equal to or smaller than 0.5. All right, that was about AND and OR. And I want you to stop this video and think about how you can implement NAND and NOT gate using the same perceptron model. Try to find out the values of W1 and W2 and the bias or the threshold. Okay? Think about this on your own. Okay, now I assume that you've all solved these two problems on your own. And let's talk about the solution together. And one note here is there might be different answers. And if your answer is different from mine, don't worry. Okay, there can be various answers. Let's first talk about NOT gate. Here we have just one-dimensional, one component from the input. We're going to have just one W1. And we are going to set this value as -1. And the threshold is going to be -0.5. In this case, if you multiply -1, it becomes 0. And because this one is larger than -0.5, it's going to become 1. In this case, it becomes -1 because 1 times -1 is -1. And this value is smaller than -0.5. Therefore, it's going to be 0. And in the case of NAND, we can set the values as -1, -1, and -1.5. And we can draw a line this way. And it will become NAND. The next gate we want to implement using our perceptron model is XOR gate. What is an XOR gate? The output becomes 1 and 1 when the inputs are different and becomes zeros when the inputs are the same values. And how should you set W1 and W2 to implement this gate? The fact is, you cannot implement this XOR gate using our perceptron model. Why is it so? As you can see here, there are 2 points, and you cannot separate them using these lines. You can draw all kinds of lines, and I'm sure that you will fail. And visually, it is quite obvious that XOR is not linearly separable. By the way, how can he formally prove this? Can he even prove this formally? And the answer is yes. And we're going to using the concept of convexivity to prove that we cannot solve XOR problem with linear classifiers. What is a convex set? A set S is convex if any line segments connecting 2 points in S lies entirely within S. Then we say this set is S, convex. Mathematically, for 2 points inside this set, we just take a weighted sum. However, this lambda and 1 minus lambda sum to 1. And lambda is between 0 and 1. After we do this weighted sum, if the resulting point is still inside the set for all x1 and x2, then we say this set is convex. And the thing is, half spaces, for example, decision regions, are convex sets. So what are decision sets? So this is an example of decision set, dividing the entire area into two. So this one and this one, like this. And decision sets or half spaces are convex sets. And let's suppose that there was a feasible hypothesis, meaning that you could find one. And if the positive examples are in the positive half space, then the green line connecting the 2 points must be in the positive half space as well. Similarly, the red line must lie within the negative half space as well. And as you can see here, these two lines intersect with each other. And because half spaces are convex sets, they should not intersect. Therefore, we reached a contradiction, meaning that we cannot solve this problem with linear classifiers. I want to mention some historical remarks. Linear classification shows some promising results in the 50s and 60s on simple image classification problems using the perceptron we discussed. However, the limitations became clear very soon. As we saw, the XOR problem looks very simple to us. However, we cannot solve this problem with our linear classification or linear classifiers because the model capacity was limited to linear decisions. And this was not the only reason. However, this was obviously one of the reasons led to decline in neural net research in the 70s. By the way, are there no ways to solve this problem? I mean, these XOR nonlinear problems using perceptrons? The fact is, we can solve using perceptrons. When you look at these data points, you need to divide these two classes using two circles if you want to stick to Cartesian coordinates. However, if you transform this data into polar coordinates, then you can simply use a line to divide these two regions. Therefore, if you come up with the right or correct representation, then you can sometimes solve some problems, nonlinear problems, very easily. And the question is, how to choose the transformation? It could be very hard in practice because we have all these types of various data and they have all distinctive characteristics. Yet, this was the dominant approach until the 2000s, like vision or speech. And what the researchers had done was designing different types of transformation for various types of data specific to certain domains, and then solve these problems using linear classifiers. But in the era of deep learning, and in this class, we want to learn those representations automatically rather than manually. But the thing is, we humans need to choose the right function family, otherwise it will fail. Here, before we move on to the next slide, I want to mention this fact. Some people say that neural networks or deep learning algorithms are just black boxes. Black boxes. And what they confused about is you just need to collect a lot of data and you just put these data to the black box and it will automatically perform well. However, that is apparently not the case. Here, as this statement states, we need to choose the right function family, meaning that we need to design the data flow. We need to design the data flow in this black box. And if we don't correctly configure this black box, then even though we have so big data, it will not work. And in this class, we're going to learn what types of data flow we need to choose to solve our own problems. So don't be confused that deep learning research is just simple and easy to solve once we secure a big data set. That is not the case. Even in that case, you need to choose the data flow. You need to design the data flow in the black boxes. Yeah, let's move on. So we can solve this XOR problem by combining or designing a nonlinear feature. Here, we can simply make x1.x2 as another feature that gets fed into our perceptron. And as you can see here, rather than having two features, from these two features, we come up with another feature. And we can solve this problem in this way. And after we transform our problem from 2D to 3D, we can simply design this hyperplane. And we can divide these points successfully. Therefore, to solve nonlinear problems, we can come up with nonlinear features. And these nonlinear features allow linear classifiers to solve nonlinear problems. This one is quite analogous to polynomial curve fitting. And the second approach is we can use nonlinearities to model arbitrary complex functions. And we can inject this nonlinearity to our perceptron. In our naive or simple perceptron, we didn't have this nonlinear activation function after this weighted sum. However, we can put this nonlinear activation function after this weighted sum. Here, this weighted sum is represented as G. Simply y hat was W transpose X plus B. Now we are having another layer, which is G. And the third approach that we can tackle the nonlinear XOR problem is by stacking multiple gates in this way. So XOR could be solved by first employing the OR gate and the NAND gate, and finally the AND gate. And it's going to become XOR. So using NAND and XOR, we can divide these two regions in this way, and we can successfully differentiate these start points from these circle points. So these are three ways we can solve this XOR problem. At this point, I want you to give this poll question to check your understanding. Stop this video and solve this problem on your own, and then move on to the next section. Okay, let's solve this problem together. The answer is 3. I told you for the first option, I told you that we could use the concept of convexivity to prove that the XOR problem cannot be solved with linear classifiers. And for the second option, I gave you this circle picture, and this could become these two lines when we change the coordinates from Cartesian to polar. So the second option is also correct. And the third option says early AI researchers parameterize the function. This is correct. And learn the parameters from data. This is quite not the truth, because we chose W1 and W2 by ourselves, not by automatically. And simple perceptron models are equivalent to linear classifiers, like WT X plus P. This is another type of linear classifier. All right, then let's implement these gates together and deepen our understanding. First, let's import necessary libraries. First of all, NumPy. And here I would like to introduce another module called DocTest. This is very important. And we're going to draw some plots, figures using PyPlot. I'll describe what DocTest is right away by discussing basic gates. Here, we're going to define the end function. And before we implement this end function, what we want to do is we want to describe the test cases first. And you may have seen this symbol when you are running Python using some interpreters. Here, you are giving some inputs to this function. And at the next line, you put down the expected output. So when this one receives 1 and 0, it should output 0 as well. And 0 and 1, it should output 0. 1 and 1, it should output 1. Maybe you saw this before when you're doing some homeworks. And after you implement this function, you check your implementation using these test cases. And when we want to run these test cases, what we can do is call doctest and run docstring examples like this, and pass the name of the function we want to test. And these are some configurations to run this doctest in this Colab environment, so don't worry too much about this. So let's say we're just returning 1 all the times, and that is our implementation. And when we run this doctest, it says, oh, when AND gates receives 0 and 0, the expected output is 0. However, it returns 1. So maybe you need to check your implementation. That's what this doctest is about. And this one goes through all these test cases and let you know where we went wrong. And I recommend using this doctest for developing your programs, because by writing these test cases, you can deepen your understanding of the function or classes you are trying to implement. And by the way, you can use this docstring or doctest approach even for classes. So you can use this approach for developing your programs. And this approach is called test-driven development. This is very famous and important paradigm for developing your functions. Anyway, that was a short introduction of doc test. And there are many other ways to use or utilize to implement this test-driven development. There are various types of libraries you could use to practice test-driven development. All right, that was short introduction of test-driven development. And let's talk about, let's implement this function together. To make the operation efficient, we're going to first turn the input into an array, NP array. And we're going to define the weights, W1 and W2, for our perceptron. And we're going to set the bias as minus 0.7. And we calculate the weighted sum using NP sum, W times X plus B. And if this temp value is smaller than 0, we're going to return 0. Otherwise, we're going to return 1. That was our implementation. And if we run this test again, it shows nothing, meaning that all the test cases are passed. And another thing is, you don't have to put this else here. You can just put return right here, because when this program reaches this point, it terminates. So these two return statements cannot be executed at the same time. Okay, that was AND. And we're going to talk about NAND from now on. Basically, we are going to do the same thing, writing down the test cases first. So I'll just copy this template. Here we're going to pass NAND rather than AND. And are going to copy these test cases. Here we need to pass NAND rather than AND. And NAND is not AND. So we are going to change 1 to 0 and 0 to 1. And the thing we need to do here is just changing the W1, W2 bias values. Which value should we use? Here we can put minus, minus, plus. That's all we need to do. And it will automatically become NAND. Okay, that was about NAND. And at this point, I would like to give you some PPP exercises. The first PPP exercise is implementing OR gate. I'm going to give you the test cases. Zero and 0, it's going to output 0. 0 and 1, it's going to output 1. 1 and 0 is going to output 1. 1 and 1, it's going to output 1. And implement this on your own. And the next exercise is implementing XOR. In this case, write down the test cases on your own and then solve this problem. Please do this PPP exercise on your own before you move on to the next video. It is very important implementing these functions on your own, because if you don't have hands-on experiences, then even though you think you understood these concepts, but when you actually try to implement these functions for your research or for your engineering product project, you might not be able to implement these types of simple functions.